And if we do this correctly, there are going to be no free electrons at the beginning. Okay, so we're going to start off with 4 possible reactions, but if I have to pair an oxidation and a reduction, that means there are really going to be 2 possible net reactions in the end. So there are going to be 2 possible net reactions. So what are those going to be? Well, the first possibility is going to be that I'm going to start with my solid zinc, and that solid zinc is going to have a pair of electrons on it, and that is going to react with copper 2+, which is an aqueous ion. And basically the zinc is going to give its electrons to the copper. And so what happens, what you end up producing is you produce zinc 2+ aqueous ions plus copper solid. Okay, so that's going to be one possibility. Now the other possibility is just basically going to be the reverse of this. So the other possibility is going to maybe we'll start with solid copper. So solid copper has a pair of electrons, and maybe the solid copper is going to give its electrons to the zinc 2 ions. Okay, so in this case, the electron transfer is going in the opposite direction. And in this case, what we would be doing is we would be producing solid zinc plus copper 2+ aqueous ions. Okay, but this is the way we would talk about things in 2070, not the way we would talk about them in 2080. Of course, in 2080, what we would do is we would say, well, you know, these reactions are going to go back and forth. And so there's always some kind of ebb and flow in chemical reactions. So really the way we should be writing this is that we should be thinking about zinc solid plus copper 2+ aqueous ions in equilibrium with zinc 2+ aqueous ions plus copper solid. Okay? Where we're starting at a very particular point of our reaction. Remember, I told you that we had 1 molar copper 2+ and 1 molar zinc 2+. So we're going to have where we're starting at a particular Q, and our particular Q is going to be equal to the concentration of our zinc 2+ ions divided by our concentration of copper 2+ ions. And I just got that from this equilibrium. And if zinc 2+ is 1 and copper 2+ is 1, Q is just going to be equal to 1 at this very particular starting point that I chose. So a better way of posing our question than what happens would be to say this somewhat differently. So a better question to be asking is does the reaction move, and by reaction I mean this reaction, does it move towards products or reactants? So does our reaction move towards products or reactants? Starting from the middle, which is going to be Q is equal to 1. So, and how are we going to answer that? Well, that's really simple. All we have to do is figure out what is delta G. Because if delta G is negative, that means equilibrium is ahead of us. If delta G is positive, that means that equilibrium is behind us. So what we have to do instead is ask what is delta G when Q is equal to 1. So if we can calculate our delta G, we'll be able to figure out whether we're moving towards reactants or products. So that's where we're headed with this, but let's have you do one more learning catalytics to sink some of these things into your brain. So here we go. So the enthalpy, entropy, and Gibbs free energy of a particular chemical reaction at 425 K are described by the graphs below. If you want to maximize the amount of products, which of the following would be an effective strategy? And your choices are raise temperature, lower temperature, and add a catalyst. Okay, I'll give you another 15 seconds. You guys are doing great on this one. Okay, so 64% of you got it correct, and the answer is A, which is raised temperature. Now, how are you figuring this out? Well, equilibrium is going to be right here at 425 Kelvin. If you want to go more towards the products, you want to shift towards the maximum of entropy, and you will go to the maximum of entropy as temperature increases. So you want to increase the temperature to shift more towards the maximum of entropy. If you lowered the temperature, you would shift towards the minimum of the enthalpy. So raising temperature, adding a catalyst is a red herring. Remember, the catalysts only affect kinetics. They have nothing to do with the equilibrium point, which is what thermodynamics is concerned with. Okay, so that's that. Let's now continue on. And what we want to do is we want to figure out what delta G is. And so now what we're going to do is we're going to figure out how we can experimentally measure delta G. So measuring delta G, and we're going to do this really simply. We're going to do this with a voltmeter. So a meter that measures voltages. Okay, so how are we going to do this? The trick is we're going to have to make our electrons go through a wire, okay? So our trick is make the electrons that are being transferred, so make the electrons flow through a wire, and this is going to be a wire that's connected to the voltmeter, and we're going to measure the direction of the flow. So are the electrons flowing from the copper to the zinc or the zinc to the copper? So we are going to measure the direction of this flow, and we're going to do this with a voltmeter or a voltage meter. Okay, so what is a voltmeter? Well, a voltmeter is just a meter that measures voltage. The schematic is a V with a circle around it, and it's going to have two wires that are connected to it, or two inlets. And those inlets each have a name, and it's an unfortunate name. One of them is going to be named negative, and one of them is going to be named positive. That has nothing to do with the voltages you are putting on the voltmeter. These are just names, so it's going to have two connections. And these are going to be named plus and minus. Now, if it were up to me, I would name them Fred and Betty or something like that, because it causes no end of confusion, because people think that by connecting to the voltmeter, you are setting what is positive and what is negative. No, 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 no. These are just names. So don't get confused by the names. So what is this going to be measuring? Well, the first thing you are going to be measuring with this is the absolute value of the voltage. So the absolute value of V, which is the same thing as the absolute value of the voltage. And the absolute value of the voltage tells you about the energy of each electron that is flowing through the wire, or flowing through the voltmeter, okay? And the important thing is when I tell you about the energy of each electron, that means each electron has the same energy. This is going to be an intensive property, and this is going to end up being very important. And what I mean by an intensive property, it's the property of each electron. So this is very different than when you go into the lab and you measure the exothermicity of 2 grams of sodium mixed with water. Then you measure a bunch of heat that comes off from that reaction. That is extensive because it comes from the 2 grams of sodium. Here, each electron has the same energy. And so we're talking about an intensive property, a property of the electron. That's going to come up next lecture. So that's going to be the absolute value. Then you are also going to be measuring the sign of the voltage. And the sign of the voltage is going to be telling you about the direction of the electron flow. So the direction of the electron flow through the meter. And so you have to know how to read that. And so let me give you how to decode that. And so if your electron moves from negative to positive, So if it moves from the negative side of the voltmeter to positive, then what's going to happen is that your voltage is going to be greater than 0. On the other hand, if the electron moves from the positive terminal to the negative terminal, you'll measure the same voltage, but your voltage is going to have the opposite sign, like that. Now, final thing, if there is no electron motion, that's going to be very important in electrochemistry. And if there is no electron motion, our voltage is going to be equal to 0. Okay, so that's going to be how we're going to end up measuring our delta G. But now we have to figure out how we're going to trick our electrons into flowing through our voltmeter. And so what we're going to have to do is we're going to have to set up our experiment in a way where the electrons have to go through the voltmeter. So let me show you how we're going to do that. Okay, so let's talk about forcing the electrons from our chemical reaction through a wire. And so the way we are going to do this is we are going to be separating our oxidation and reduction reactions. Okay, so how are we going to do that? Well, let's start sketching this out. And this is going to be a big sketch. So let's go on and start off with our 2 pieces of metal. So here's one of our pieces of metal. And then we're going to have our other piece of metal. And we want to separate our oxidation and reduction reactions. So let's make this the zinc. Let's make this the copper. And our trick is going to be, we are going to have 2 separate beakers. And one of the beakers is going to have the zinc solution, and one of the beakers is going to have the copper solution. So here are 2 beakers like this. We're going to fill them both up with solution. So our zinc beaker is going to have 1 molar zinc 2+. Our copper beaker is going to have 1 molar copper 2+, like that. Now, we are going to make the electrons flow through the voltmeter. So here's going to be our voltmeter up here. And what we're going to do is we are going to connect the voltmeter with 2 pieces of wire to our pieces of metal. Okay, so this line up here is going to be wires. Okay, so that's how we are going. And then we're going to have one more thing that we're going to talk about at the end of the lecture. So don't worry about this just yet, but let's say we're also going to have a salt bridge, whatever that is. And we'll come back to that. Okay, so now what's going to happen? Well, it turns out for this chemical reaction, what happens is that it's the zinc that dissolves. I can't predict that right now, but we'll learn how to do that in the next lecture. So what's going to happen is that the zinc is going to start to dissolve. So the zinc metal becomes zinc 2+, and as it does that, it gives off some electrons. So there are the electrons. Now, the electrons are going to repel one another. So as you produce more electrons, they are going to push up on each other. And so because of that, the electrons are going to push through the wire. Then they are going to push through the voltmeter. So they're going that way through the voltmeter. Oh, and I should give you some signs. So let's make this the negative side and the positive side of our voltmeter. And then here come our electrons around the bend, and then they come in here into the copper electrode. Now, what happens there? Well, now we have a source of electrons, and the copper 2+ is going to react with those electrons to be making more copper solid. Okay, so what's going to be going on in the left beaker is that our solid zinc is going to be dissolving to give us more zinc 2+ plus 2 electrons. And so because of that, this beaker is going to be where our oxidation is done. So the zinc is oxidized. And because of this, this is going to be our oxidation beaker. Okay, on the other hand, in this beaker over here, what we're going to have is our copper 2+ ions are going to react with the 2 electrons, which came from the other beaker, to give us copper solid. So in this beaker, copper 2+ is reduced. And this is going to be our reduction beaker. So notice we have separated oxidation and reduction in 2 separate beakers, and we've made the electrons go through our voltmeter. Now, the question is what does the voltmeter say? So when we look at this, what happens is we measure that our voltage, V, is going to be equal to a plus 1.10 volts. So what is this going to be? This is going to be a measure of the energy of each electron. If this number were larger, we would have more energetic electrons. Okay, so what is this thing that we have just measured? This is going to be what we call the cell voltage. So this is our cell voltage. And we are going to give it the variable E sub cell. And it is going to have units that, no surprise, are equal to voltage. Okay, and so this cell voltage is going to be a measure of the energy. So it's the measure of the energy that is going to be pushing each electron from the oxidizing species to the reduction species, or to the reducing species. Okay, so in some sense, this is really a measure of our exothermicity. So the zinc is pushing the electrons and pushing them onto the copper, and there is some extra energy that goes along in these electrons, and we're going to be able to use that extra energy to do something fun like drive your laptop, because this is a simple battery. Okay, let's do a quick learning catalytics to see if you understand what's going on in this setup. Okay, so you construct the copper zinc cell shown below. What voltage do you measure in volts? And don't add units, just give me a number in volts. I'll give you another 10 seconds to get those answers in. Okay, so 55% of you got it correct and said negative 1.10 volts, okay? So negative 1.1, what happened is the only thing that you did here is you flipped the terminals on your voltmeter. You just plugged the wires into the opposite terminals, and so nothing changed about the experiment. The electrons still go from the zinc to the copper. It's just that now that you've reversed this, the sign of your measured voltage changes. Okay, so that's that. So the key point of all of this is that this voltage that we are measuring, this cell voltage, is a measure of delta G, okay? So our cell voltage is a direct measure of delta G. Okay, but now we have to learn how to convert from delta G to what we actually measure. And the equation that we are going to be using is that delta G is going to be equal to negative nu sub E times F times E cell. Okay, so E cell is going to be what we're going to be measuring with our voltmeter. So this is what I have just introduced as the cell voltage. Then we are going to have F. F is going to be a new constant. F is called the Faraday, and one of my first graduate students named his son Faraday. Thank God it was the middle name. And a Faraday is going to be equal to 96,500 coulombs per mole of electrons. Okay, so a coulomb is basically an electrical engineering quantity that represents some number of electrons, and moles of electrons are also some number of electrons. And so those are related to each other by a factor of 96,500. Okay, now we're going to have this term that is going to be nu sub E. Nu sub E is going to be the number of electrons transferred. And this is the number of electrons transferred as written in the chemical equation. So for the reaction we're looking at, that number is going to be 2 because there are going to be 2 electrons in the reaction. And then last but not least, we know that delta G is going to be equal to the slope of G. It is also going to have units that are going to be either joules per mole or kilojoules per mole. And it's useful to know that this can be rewritten as a volt times a coulomb per mole, or in other words, a joule is equal to a volt coulomb. Okay, so this equation is going to allow us to convert from what we are measuring on our voltmeter to what we want to measure, which is going to be delta G. However, there's this pesky sign right here. There's this minus sign. So that's going to be something we need to take into account. So if delta G is equal to a negative number, so the slope is going down, you want to move towards the products. Well, if delta G is equal to a negative number, from this, it's going to follow that E cell is going to be a positive number, okay? Because there's this minus sign here. Nu sub E is always a positive number, F is a constant, and so E cell is positive if delta G is negative. And if delta G is negative, our reaction is going to move towards the products. So our reaction moves towards our products. On the other hand, if delta G is equal to a positive number, then E cell is going to be negative. Okay, so there's the sign flip here, and our reaction moves towards reactants. Okay, and then finally, and this is very important, if delta G is equal to 0, it follows that E cell is also equal to 0. And of course, then the reaction is going to be at equilibrium. But the really important concept here is that if E cell is equal to 0, this is what we know of as a dead battery, okay? So when you have a dead battery, you have a battery that has come to equilibrium. If the battery has come to equilibrium, there is not a reaction that is going to drive electrons from reactants to products. And since there's no reaction to drive, there is no energy for your laptop. Okay, so that's how we are going to relate E cell to delta G. Now let's think about this, about what's going to go on if we are at standard state, because electrochemistry, people often talk about what's going on at standard state. Okay, so if all components are at standard state, so if all components are going to be at standard state, and that's going to have two things associated with it. First, we're going to be at 25 degrees C, of course, but also standard state talks about concentration. So all of our concentrations are going to be equal to 1 molar, okay? So that's why I started out with 1 molar copper ions, 1 molar zinc ions. We were at standard state. Okay, well, if that's going to be true, then what we are going to do is we are going to take our old friend, delta G is going to be equal to delta G of reaction naught. So that's going to be appropriate if we're going to be at 25 degrees C. And that is plus RT ln Q. However, if all of our components are at standard state, which means all of our concentrations are at 1 molar, what that means is our Q must be equal to 1. If our Q is equal to 1, the natural log of 1 is going to be 0. So if all components are at standard state, our delta G is just going to be equal to delta G reaction naught. Okay. So that's what we're going to have when we are at standard state. And I should relate that, of course, to our cell potential. So that is going to be equal to negative nu sub E F E cell. But if we're at standard state, we are going to use the standard cell potential, which is going to be E cell naught. So this is going to be the standard state cell potential. Okay, so that's what we are going to have, or instead of saying standard state cell potential, I could also say cell voltage. Those two words are interchangeable, particularly in this course. Okay, so that's going to be our standard state cell voltage. Okay, so let's look back at this system that we set up and try and understand it in a little bit more detail, okay? So in order to understand this thing with the two beakers and the voltmeter and the solutions and salt bridge and all that stuff, what I'm going to do is I am going to draw it schematically, because by drawing it schematically, I'm going to take away a little bit of the detail, so we'll be able to look at what's actually going on. Okay, so let's look at a schematic of what we set up at the beginning. Okay, so when we started out at the beginning, remember that I had a piece of zinc. So here is going to be my piece of zinc. Then I also had a piece of copper. So here is going to be my piece of copper. And then what I did was I stuck my zinc into a beaker. And so I'm just going to represent this beaker that has solution in it by this dotted line like this. And so I also had some zinc 2+ in my beaker. And then I had a second beaker. So this is going to be a second set of dotted lines. And so in this beaker, I also had some copper 2+. Okay, so that's going to be my two, those are going to be my two beakers. Then I'm also going to have my voltmeter. So here is my voltmeter, and it's going to have two leads named negative and positive. And then what I do is I connect my zinc to the voltmeter with some wires. So I take that wire, and then I put another wire like that. Okay, so that's going to be how we are going to be setting up. And so what we have then is we have the left hand is going to be our oxidation beaker. And the right hand is going to be our reduction beaker. Okay, so what is going to be going on there? Well, remember that what I said was going to happen was that some of the zinc was going to be dissolving to be making electrons. So there are electrons coming off and making our zinc 2+ like that. So zinc is dissolving to make electrons and zinc 2+. So in this beaker, what I am having is charge separation. Okay, so the zinc 2+ separates from the electrons. Now the electrons come out through the wire. So there go the electrons, and then through the wire like that. Then they're going to go through the voltmeter, and then come out to the other end, around the corner, and then they are going to go in. Now, so here come our electrons into this reduction beaker. What's going to happen now is that the copper 2 plus is going to react with those electrons to make more copper. So in this case, what we have is the electrons recombining with the copper 2 plus. So here we have charge combination or charge recombination, however you would like to say it. Okay, so that's going to be what's going to be going on. However, when you look at it like this, you can immediately see we've got a massive problem, because what's happening is we just look at what's happening outside of these beakers. Electrons are leaving this beaker and they're going into this beaker. And so that's a big problem. So this beaker is becoming positively charged. This beaker is becoming negatively charged. It has extra electrons. So we have just set up something that has a big problem with it. And the big problem with this is going to be that we are draining electrons from our left beaker. So we are draining electrons from the left beaker. Now, why is that going to be a problem? Well, if we're draining electrons from our left beaker, if we keep removing electrons, this beaker is going to become positively charged. And as you try to remove electrons from something that is positively charged, it's going to get harder and harder and harder, because separating an electron and a positive charge takes energy. So what's going to happen is that this reaction is going to start, but very quickly, you're not going to have enough energy to remove the electron, because it won't be able to escape this positive charge. And so we're going to have to do something about this, and we must balance our electrical charge. So we must balance our charge. And the way we're going to do this is we are going to use something that is called a salt bridge. Now, what is a salt bridge? It can be many different things. A very simple one would be to just take some sodium chloride or some salt and mix it with Jell-O. Or you could do something even simpler, and you could just use a pickle. And pickles are great salt bridges, okay? So here we are going to put our salt bridge. And of course, a pickle is just a salty cucumber, so it's not that different from salty Jell-O. And so what's going to happen now is we're building up a positive charge on this beaker, and we are going to have sodium ions, and we're going to have chloride ions in our salt bridge. And so because of this, the chloride ions are attracted to the positive beaker, and the sodium ions are going to be attracted to the negative beaker. And so you can see what's going on now. If you look at this, chloride goes to the left and electrons go around like this. And so what's happening here is that all of our negative species are going clockwise. So this is going to be our negative species here. And what are our negative species? Our electrons and our chloride ions. On the other hand, anything that is positively charged is going to go in the opposite direction. It's going to go counterclockwise in this case. So our positive species go in the opposite direction. And so, for example, you can see that our sodium ions are going to the right, but it also turns out that our copper 2 plus and our zinc 2 plus are also going in a counterclockwise direction. Okay, so this is how we are going to balance charge in this. And with that, let's leave it at that. And I will be happy to answer any questions that you might have. And have a great rest of your day.
Thank you. Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Hi.
Hi.
I was wondering, you mentioned earlier that the voltmeter would measure like the absolute value of voltage, or that if you flip the
So let
terminals.
me say that better, okay? The voltmeter tells you two things. one, the absolute value of the voltage tells you about the average energy of the electrons. Second, it also tells you the sign of the voltage. So they both come out. It'll say like minus 1.1 or plus 2.13. The sign tells you, are the electrons going in this direction? Are they going in that direction? So those are both pieces of information in the number that you read off of.
Okay, thank you. I was a little confused about that.
Sure.
Thank you.
I have a question. Does electronegativity affect the metal's ability to either take away the electron or accept the electron?
Yep, and we will see that next lecture.
Okay, and I have one more question. When you were talking about forcing the electrons through the wire, you used the term exothermicity, but can you elaborate kind of what you meant by that? Or
Sure.
what the difference between, yeah.
The reason that the zinc is giving up its electrons to the copper is because the reaction is exothermic, okay? And so that's where the energy is coming from that is pushing the electron around this circuit. So that's the energy for the battery. If this reaction were general, endothermic reactions don't go. Now, instead of saying exothermic and endothermic, technically, I should be talking about whether it's endo-free energy or exo-free energy. And that's what I'm talking about when I talk about the cell voltage. So instead of talking thermicity, I should really be saying free energy. But to a first approximation, exothermic reactions go in the forward direction and endothermic reactions go in the reverse direction. Not always true. You have to look at the free energy, but that was what I was trying to convey.
Got it. Thank you so much.
Sure.